Today we'll talk about DC circuit. DC meaning direct current circuit, as opposed to alternating current, which you don't know yet. I'm not sure if we will ever get to it, but direct current, your battery, rechargeable battery or otherwise. So that kind of current, that circuit. Okay, first we have to define current. What is a current? It's a movement of free electrons in a conductor. And that's pretty obvious, isn't it? Because we know now if there's a battery, then electrons will come out of this negative end and start traveling around in this direction and go into the positive end. Except there's one problem. Because when Ben Franklin figured out electricity, he had no idea about free electrons. So he thought it was a positive charge that's coming out here and moving around this direction. We can think of it as positrons moving, except physically that's not what's really happening. So people make this kind of a little thing. You know, if there's an electron that's moving away from this point, away, right? And then that leaves a hole here. And the next electron hops in here, then that leaves a hole here. So the hole travels on the other direction. It was like, whatever, right? We don't have to think like that. We'll just say the positive charges are moving because everything, entire electrical engineering is built like that. And we're stuck with it forever. So it's easier to think conventional current as opposed to real current, which is free electrons in a conductor. You do know that free electrons can move in a conductor, right? So that positive charges are moving from positive end to the negative end. This is some kind of power source, any kind of rechargeable battery would do, or chemical battery. So that's a current. Okay, so this is the definition of current. It's a rate of charge moving, passing through some kind of net cross-section area. You know what I'm saying? So that makes perfect sense if we just define it as a derivative of the charge, whatever the charge is moving, and then we'll get this. So if you want to figure out the net charge passing through any circuit at given time, we'll just do something like that from T0 to T1, right? So current is the derivative of the charge. And the unit of the current, this is called ampere. The guy who figured this thing out. And this is, of course, coulomb, and this is second, right? Because derivative. So coulombs per second is what ampere is. And then 1 ampere is huge amount of current. So realistically, we use milliampere a lot. Okay. Alrighty, moving on. Then what is a resistor? Okay, I'm going to draw a circuit diagram here. So let's say, and this is a symbol for battery, and this is a symbol for resistor. Okay, so our current will flow through in this direction. Okay, and this resistor R, and this is battery, which gives some kind of potential difference. Remember, this is higher potential and this is lower potential. Therefore, these charges are forced to move around like that. So when you're thinking like this, it's easiest if you imagine pipe of water, and we put some kind of a water pump here. So it's supposed to shove the water in this way, and then it's going through some kind of filter, water filter or otherwise, whatever the sponge and thingy made of. So this is the picture you want to imagine. So this pump will push water this way, so it will create higher pressure here, right? And then here is low pressure compared to this end and that end. You know what I'm saying? And then it'll go through. If without this filter, the pressure throughout the pipe will be exactly same because it'll just flow through and then fill it to the other side. But because this thing resists the water molecules to pass by, then it will be higher pressure on this side of the pipe and then lower pressure on that side of the pipe. And that pressure difference is our voltage, also known as potential difference. People call this voltage. That makes sense to you? Now, then so resistance is defined like this. Your potential difference divided by the amount of current that is allowing to pass through. So obviously, if resistance is big, then amount of current will be small. That makes sense from this relation? Yeah. Which one? Oh yeah, oh, this symbol. Yeah, this is by definition, that is what is equal to. Also, mathematicians use this symbol a lot, but we'll just go with whatever the book uses, okay? That means by definition, it's defined to be like that, okay? So this makes sense, right? And then, of course, the other relationship we want to think about it, this thingy, is delta V is equal to IR. We'll be using this form a lot. Okay, so this is some kind of current, is some kind of direct variation between R, right? So if you have more resistance with this thing being constant, then current has to reduce and vice versa. Okay, so that's how it. So when we measure by the way, later, in case you do a lab or do a lab type of problem, when you measure the voltage, they say potential difference, here's a voltmeter, some kind of meter, you want to put these two wire from here. It's always across something. And voltage here is going to be exactly same as voltage there, right? But higher potential, and free wire is same as a pipe without any resistance, so these things just flow. So it's always the same. When you measure the amperage, also known as the current, you always want to put it through here. So how much of water passes through this thingy right there? You get it? So that's how you're supposed to arrange the circuits. Okay, so then physically, this resistance, what does it depend on? Think of it as a water filter again. If it's wider, then more water will go through, right? And then if it's longer, then it'll be harder for this water current to go through, right? So that makes sense that this resistance is proportional to, and this is some constant of proportionality to the length of the resistor, but inversely proportional to the cross section, right? The resistance is kind of like restricting water. So water is less likely, current is more difficult to pass through if it's longer in physical nature, whatever the material is. But if it's bigger cross section, then it's easier for the current to go through. Okay, and this constant is known as resistivity. Let's learn to speak resistivities. Oh my God, that's a mouthful, right? And then here, this table, just for your reference, copper is one of the better. So smaller this is, it's like reciprocal of conductivity. So if this number is smaller, then it's a better conductor. Get it? And silver happens to be the one of the best conductor there is. And then it also has to do with the temperature, and then copper, and then gold, aluminum, and then these things, right? So what do we use generally inside the wires, electrical wires? Do you know what kind of material they use? They use copper. Why not silver? Because silver is so dang expensive, right? Copper is a lot cheaper than silver. It's almost as good, but it's a lot cheaper. So they use copper a lot. And then you go down, and this is like insulator, right? Things like this do not really let the current. With enough current, it will still go through. With enough voltage, if its voltage is potential difference is strong enough, it will still go through. But for all practical purposes, these are insulators. Okay. Okay. Then electric power. Let's talk about power. Okay. So our work, remember, is Q times the potential difference. Do you remember that thing from our previous sessions? Oh no, you don't remember, right? Okay, this is Q times integral of E dot ds. And this is what we call potential difference. You know what I'm saying? Okay, so that's what work, or also known as energy, right? Oh, let's not put E because there's E electric field. So work, whatever, energy, potential energy or whatever, okay? Let's define power. Power, trying to be fancy, is defined to be the derivative of work or energy. So rate, how fast can you do the work? You know what I'm saying? So if it's a constant value, then you just divide by T. Good? Okay. Now, let's say this potential difference is constant. This is usually the rechargeable batteries or your 1.5 volt batteries gives the constant voltage out. So it is pretty much constant for all practical purposes. Although in case of discharging capacitor, it goes down, but let's not worry about that at the moment. Then this is constant, so you take a derivative of Q. Good. What was the derivative of charge earlier? Oh no, that is what we define as current. Okay, so power, I have it here, happens to be I times delta V. Or many people, many books drop this delta, so IV. Okay, so that's what power is. Okay, now, then we are going to do something. Remember earlier that V, delta V, was equal to IR, right there, right? Right here. Let's substitute that in. If you substitute that in, then our power becomes I square R, correct? Too much algebra? Tell me you're with me. Okay. Also, the power, we can use the other relationship. I, let's say, is equal to delta V over R, right? And substitute that there. Then this power can be this form. Right? If you have this, why would you want to do such a thing? Usually, you don't want to calculate both of them. It's many cases, this is given. This is easy to detect because you plug it into whatever the battery. And this, in a lab, it's like resistor has the resistance written on it. There's a color code. So this is easier formula than calculating I, then multiplying by potential difference. So people use this a lot. Okay? Now, let's learn if the bunch of resistors are put together in a circuit, what is the equivalent total resistance? Okay? So we have this. But if you just think conceptually, so two light bulb resistors typically is a light bulb or anything that does the work, your device, they all have resistance, although they are called impedance. But for our purpose, it's the same thing. So the current has to go through this one and then this one. So the arrangement is like this, two resistors. But our resistance is directly proportional to the total length, so that you will just add these two. It's the same thing as this thing just connected together. So you would think your R equivalent is equal to R1 plus R2. And in fact, that's exactly what it is. Okay, let's reason though. Okay, because later this reasoning skill comes in handy later when we do Kirchhoff's law. So this is higher potential, positive side, and this is lower potential, right? Current will go through here. Water pressure difference, right? So this is higher, let's put 2 plus signs, and this is lower, 2 minus signs. That much is easy to see. But this point A compared to point B, which is higher. Point A has to be higher than point B. It goes down a little bit, maybe 1 plus sign. You know what I'm saying? Or neutral, 0, whatever it is. It has to be lower because water has to go through this sponge or filter. So now the pressure here is lower than this part. Then it has to go through that part again. Then it goes down. You know what I'm saying? So same amount of current, water that went through this has to go through this. So your I is throughout same everywhere. However, the potential difference, if you measure it, delta V here and delta V here, they have to add up to the total pressure difference between these two ends. That makes sense to you? So if you put this thing here, delta V total, from here to here, has to be same as these two together. So we'll say delta V total or equivalent is equal to delta V1 plus delta V2. So far so good. But then remember delta V is equal to IR, right? So the total current is exactly the same everywhere. Same amount of current has to go through all of these. So I total R equivalent, those of the resistance put together, has to be same amount of current and then R1 plus that current times R2. Divide both sides by I, then you get R equivalent is equal to R1 plus R2, which is exactly what we have reason to be. Okay, so if you put more than one, then you just add them up. But that's the easy case, which was kind of, well, we'll talk about comparison to capacitor after this one. What happens if we put two of them in parallel like this? Okay, so actually, realistically, this is the arrangement. Okay, now this I here will have to split into two different directions, right? So already you see that I here is equal to I1 plus I2, right? Water has to divide into two separate, depending on how resisting these guys are. If this is stronger, then more will flow through I2. If this is stronger, then more of them will flow through that one. That makes sense to you? Okay, however, let's look at the potential difference. The water pressure in this pipe has to be exactly same as the water pressure on that pipe, wouldn't it? If it's not, then whatever's remaining charges or water will just prefer to go around. They are free to move around this empty wire, correct? So potential difference has to be exactly the same if you measure it here, here, or here. You know what I'm saying? So that is the key here. Good? Okay, then we'll say I is equal to I1 plus I2. But now remember I is equal to delta V over R, wasn't it? Substitute that in, so we have delta V total over R equivalent, right? Equivalent resistance of these two together is equal to your delta V, same thing as here, over R1 plus delta V over R2. And divide both sides by delta V, then you have this. Okay, now let's contrast this with capacitance. Because remember when capacitors were in parallel, remember, just put it in parentheses, C equivalent was equal to C1 plus C2, wasn't it? It's exactly opposite. And here, when capacitors were in series, then this used to be like that, wasn't it? So resistors and capacitors behave exactly the opposite ways. Okay, and this is not just formula, but that happens to be through physical reasoning. Good. So this is the total where resistors in parallel. Okay, those are easy enough now. Okay, let's move through and calculate one still pretty easy enough, but this type of equation. And then the APs will make the circuits a whole lot more complicated. Okay, so we have to find the total resistance as if this is a hole at 1 inside the box. Okay, so first thing is we identify this part first. One is in parallel. Okay, so we'll calculate that one first. And the way we do it is 1 over R, what do you want to call it? Equivalent, whatever, is equal to 1 over 6 plus 1 over 3. Good? Is that 1/2? Which means R equivalent here happens to be 2. What's this symbol? How do you read it? This is ohms. This omega, Greek symbol omega, because O was already, O is not a good symbol to use for any unit. So this is the unit of resistance. Okay, so 2 ohms, 2.0 ohms to be correct with the sig fic and everything, although I didn't really do it there. Okay, now, then you just forget that thing and then you redraw the circuit or reimagine the circuit. That's also ugly. So this is 8 ohm, and this is 4 ohm, and this we just calculated to be 2 ohm, right? So the total resistance is adding these together. You get it? Okay. You notice that this is 6 and this is 3, but if you put 2 of them in parallel, it's smaller than either one. And that makes sense because remember resistance is inversely proportional to the cross-section thickness. But so if you put them in parallel, you're in fact making both of them wider, thicker. You know what I'm saying? So that physically makes sense too. Good? Okay, any questions at this point? Okay, then moving on, let's talk about EMF. There are so many definitions in this unit, so math-wise it's easy. You just need to remember a whole lot of it. Electromotive force, number 1. This is not a force. I don't know why they named it like that. It's just potential difference. It's a voltage out of the battery. Okay? But this battery, let's say this is battery, 1.5 volt, right? 1.5 volt, they say. And then there's a chemical inside that creates this. But the battery has an internal tiny bit of resistance. This is very tiny amount, but nothing has a zero resistance. So battery itself has a built-in resistance. You know what I'm saying? So you have to lose a little bit. So this EMF, fancy cursive E for EMF, happens to be slightly higher than 1.5. That makes sense to you? So you lose a little bit. Remember in parallel, the water pressure from here to here is different and then go through. So you lose a little bit. So EMF realistically inside the battery has to be slightly higher than whatever the voltage is outside of the package. So graph-wise, this is the amount of EMF, and then you lose a little bit because of this is inside the battery, internal wiring. And this part, IR, this is what we commonly known as delta V. Okay, so it's like some problems like calculate the EMF, internal resistances, whatever, right? So this is the situation. So far, so good. And then they, as if this is not confusing enough, they use this as if it's the voltage of the battery. And many times they are saying this is so small, it's practically zero. Okay, so that's so far so good. Those are the easy definitions now. Now we'll talk about Kirchhoff's rule. Kirchhoff's rule is when you have a circuit that looks like this, now how are you gonna calculate it? Right? I is equal to V over R, except which V are we using? There are two batteries. Right? Oh, even this case. Two batteries, but they're fighting each other. Which one wins? By just looking at it, this one is a stronger, so this one has to win. So realistic current will go through this direction, right? So this is easy enough to see. This is just a practice. But here, where is the current going? Probably in this direction, that direction. So these two will merge in like this. You know what I'm saying? Yeah, but then there are so many cases that there's another battery here and capacitors around. Things get really clogged up. So physicist named Kirchhoff has come up with a handy way of calculating this. Number one, junction rule. They say all of the current must add up to zero. What that means is, let's look at this diagram. Here, I1 plus I2 is same as old I's. This is I1, right? I1 is equal to I2 plus I3. That makes sense to you? Because it has to split into these two. Or when the current merge together, then just two of them add up to. So that makes sense. It's like if you think water, right? All this water have to split into those two, whatever the amount. Okay, so that's easy. If you draw a closed loop and total potential difference has to be zero. What? What does that mean? Let me draw a simple circuit here to demonstrate this idea. Okay, so let's say this is delta V and this is R, right? And there's a current flowing in that direction, right? I. Let's see if we get V is equal to IR. When you draw this, let's go through this battery first. So if you go from this side to that side, does your potential go up or down? Remember, this is high side, and this is low side, isn't it? So you gain potential. So positive delta V, and then from this side to that side, does your potential go up or down? High, low. It has to go down, right? So that one is minus, and then what is the, I told you delta V is equal to IR, and that has to be zero is what this thing is saying. Otherwise, they will all balance out. The free electrons will flow to balance this thing out, so the total net has to be zero. And from here, we get exactly what we had earlier. Good. Let's apply them to a little slightly more complicated circuit. Two batteries. Realistically, if you have both two water pumps fighting each other, then it will go through this. Current will go through the battery in that direction. Realistically, it will go through that direction. And it will actually fight through this battery. Okay? However, say we screwed up. And we decided, we didn't know any better, so we decided to put the loop in that direction. Okay? Then we'll write this out. Okay? And here they are using this EMF symbol as if this is just a potential difference, meaning internal resistance is zero or close to zero. Good? So E1, do we gain or lose potential in this case? We gain it, right? It's a higher potential on that side. If we decide to, say, go that way, and then from through this, we lose potential, right? Higher, if we assume we screwed up and assume this is like that, although it's the other direction. So you lose potential. So minus I times R1, because IR is equal to delta V. Okay? Now you have to go through this. So from here to here, are we gaining or losing potential? This is definitely higher side than this. So this one, you have to write it as negative. That makes sense to you? Okay, and then here, you lose again when you go through this. So minus IR2 has to be zero is what Kirchhoff's law is saying. Okay, so here's the rule. Every other thing, resistor or capacitor, if you go through, you just drop the voltage when you draw the loop. Only thing you have to care about, everything is minus except batteries. Batteries, you have to decide a little bit carefully. Are we gaining potential or are we losing potential? This is gaining if you go through this way, higher, low to high, compared to high to low. That's the only thing we have to be careful. Good? Now, the problem says calculate the total current in the circuit. Like terms, so do you see I and then R1 plus R2 on the other side is equal to E1 minus E2? Too much algebra? No. Then I happens to be, this is simple enough, we can do it with symbols, but next example is not so nice, so we are not going to do with symbols, right? And then this is 6.0 volt minus 12.0 volt over resistors, 8.0 ohm, that's ugly ohm plus 10.0 ohm. Is that negative 1/3, right? See, we screwed up and didn't decide the direction of the current correctly, but Kirchhoff's rule still gives you, no, 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 it was not that way, it's that way, right? 0.33 with a sig fig. You get it? So that's what Kirchhoff's rule allows us to compute. We are computing the current at any part of the circuit. There's only one I because everything is connected. Now let's practice this on a more complicated circuit. Holy cow, right? So first, we'll figure out the junction rule current. Okay, I guess we'll have to say this way, but then that one that way, so that way. You see how confusing this is, so forget it. We'll just say this is loop 1. Okay, and this is loop 2. We just arbitrarily decide kind of from this example we saw it doesn't matter which direction we decide. This will tell, oh, negative. This will tell us if we screw up. So we really don't care. Okay, so this is loop 2. With me so far? Okay, so current first. Current is easier to figure out. If we decide to go that way, then these two, I1 and I2, must add up to I3. Good? I1 plus I2 is equal to I3. That makes sense to you? You'll see why pretty soon, but you want to write it like that, according to our junction rule. Okay? And then loop 1. We'll look at loop 1 here. Okay? So let's decide carefully. From here to here, are we gaining voltage or are we gaining potential or losing potential? We're losing it. We'll call this E1. So we have negative E1, negative 14 volt, right? And then I2, and this is I1, here to here. Are we gaining or losing? Oh, this we have to be slightly, I never liked this loop anyway, but this is higher potential and this is lower potential. So we're gaining it here, right? I1, R1, we'll call this thing R1. I know, I have a better way, but this is how the book does it, so I did it this way, and I'll show you an alternative which is infinitely better than this, okay? And then, from here to here, are we gaining it or losing it? Now we are losing it high to low, so this is minus E2, we'll call this thing E2. So far so good. And then here to here, we are losing it again. Minus I, this is still, this part is I2, right, that part, so I2, R2, we'll call this thing R2. And that needs to be 0. So far, so good. Let's plug in the numbers. So this is negative 14. We'll drop the voltage sign and sig fig for the simplicity, for our sanity. And I1 and 6. So we have plus 6 I1. Good. And then minus 10. And then minus, this is 4 I2. Good. With me? Okay, so cleaning up, so you have 6I1 minus 4I2 is equal to 24. And you can divide both sides by 2 and do all that, except we're not going to do that. There's a reason. You see what this is becoming? This is 3 by 3 systems of equation. I1, I2, and I3. Oh no, tell me it ain't so. Well, let's do this. So this is loop 2. So we start here. Is it gaining? Right, so that's gaining voltage. And then you lose some here this way now. So that's minus I1 R1. And go around this way, then you lose some more here. And we'll call that R3. So we have minus I3. I tend to name the resistors after the currents that I decide. I mean, this I'm using the Brooks diagram, but if you decide to call it 1, 2, 3, then try to name the resistors the same way. That's according to the Kirchhoff's rule. Question?
Can you explain why I1, R1, and J1 is gaining?
I had to think about it a little bit, but because of this battery right there, this side is higher than that side. I'll give you an alternative so you don't have to think like that, okay? I never like this. So let's plug in numbers. So this is 10 minus, what was it, 6 I1, and minus, this is 2 I3 is equal to 0. Then 6I1 space minus 2I3 is equal to 10. I'm going to call this equation 1. I'm going to call this equation 2. And I'm going to call this equation 3. Then we have 3 by 3 systems of equation. Yes? This is plus. Oh, you saved me. Otherwise, this is this. If you know, remember the matrix? Yeah, we are using matrix, but matrix chapter from pre-calculus, tiny little mistake we'll just make, right? Okay, so what we have here is, we'll set up the matrix equation, 1, 1, negative 1, second line, 6, negative 4, 0, and third line, check my writing, 6, 0, 2. Did I do this correctly? Let me check. Yeah. And then we have I1, I2, I3, and the other side, the voltage. So this is, yeah, AX is equal to B thing. You know what I'm saying? And this is 0. We have 24 and 10. Now we take up the calculator. Because we're not going to do this by hand. Gauss, Jordan, eliminate? No, God, no. Right? Remember, physics is always calculator, correct? So we press matrix button, and then we enter it into A. I already entered it in order to save time before you showed up, but compare this to that, correct? Okay, with that, and then matrix button again, and you edit B. And then you enter this 0, 24, 10. Then, of course, you all remember what to do. Matrix button, A, inverse. Oh, old eyes. This is inverse? Yeah, thank God. I was just going with the 50% probability right there. Matrix button, and then B. Bang, huh. This is the most efficient way of doing Kirchhoff's rule. Especially, you will be dealing with decimals anyway. You do not want to do this by hand. Although many books explain it by hand, like no, 2, negative 3, and 1. So this thing tells you your I vector is equal to 2.0, negative 3.0, and Was it positive 1? Negative 1, right? And how's that? Yes. I think your teacher wants 2 digits, right? Oh, whatever. Okay. And now, according to this sig fig we're given, this is correct. Now, so looks like we screwed up a couple of them, right? I2, actually it flows that way. And that makes sense, that battery is there, right? And I3, it doesn't flow this way, but it flows that way. You know what I'm saying? So these two merge, these two will merge and then go that way. It's a realistic, these merge like that. It's a realistic picture. Kirchhoff's rule takes care of us, so we don't have to worry about it. Okay, now here is the alternative. Okay, because this is a confusing loop, isn't it? Instead of this. So let me propose this. Realistically, this, I'm going to do it with a different color, blue. This is loop 3. And I'm going to put it in this direction because that battery, right? Yeah. Okay, then I'm going to do loop 3 on the side. Don't have space. Uh-oh. Down. I'm going to do loop 3 at the bottom. Loop 3. Okay. So E1, we're gaining, right? So E1 is positive, and then we lose voltage here. So we have I2 minus I2 R2. Good. Through this. And then here we lose again, right? Minus I3 R3 is equal to 0. And that's a whole lot more straightforward and easy to calculate, isn't it? And then from there, we plug in numbers. So this was 14. 14 minus 4I2 minus 2I3. Good? Wait a minute. Something is screwy. This is not going to give me the right answer. I'm going that way, so I gain, right? I'm getting confused of myself. I want this to be negative, but not going to give me that. Will it work? Hold on. Let me check my matrix.
I think it works if loop 3 is pointed in the right direction.
Huh?
I think loop 3 is in the direction that would make it positive.
Loop 3 is... I put the loop 3 in the wrong direction, didn't I? Right? Let's put loop 3 into this direction. Right? Because everything else, otherwise we have to change the sign for everything else. You know what I'm saying? So let's put it in that direction. So only the difference is then that becomes negative A. And then this becomes negative. I think this will work better. Then we can keep, otherwise, I mean, we could have done it that way, but then we have to worry about all other loops, and I really don't want to do all of that. Okay, so here's a revised matrix. And this is my equation 4. And so we only need to switch this thingy, right? So let's recycle our work. Okay, copy that and paste it here. Change the color. It doesn't want to change the color. Great. Actually, I'm going to change the color in the middle one. How's that? That I need to erase. And then I need to replace this by 0, 4, 2. You know what I'm saying? And then the other side I have 0, so this is negative 14. And solve this system. Okay? I already entered it, I believe. Not like that. Clear. Clear. Second matrix button, edit, and I saved it here. Is it correct? Okay. And then you enter the other vector, in which I saved it into D here. Good? Now, quit. So if you do matrix C, inverse, oh, which was inverse again? That one, right? Yeah. And then this thing and D gives you exactly the same answer. So when you draw these loops, I will always try to draw everything in consistent same direction, but do it in a way to only put one battery in it. And that way, it's a lot less confusing. You don't have to think about it a whole lot. Okay, sometimes it requires 3 different loops. Then you have a 4x4 systems of equation. But in this case, it worked out. Yes?
In this one, it's going clockwise.
Yeah, everything is in clockwise motion.
And that means like the middle will go to the left.
This, yeah, middle will go to the left.
And then on the bottom one, it goes to the right.
This, yeah. On this next one, yeah, this in loop 2, it goes to the right. So that kind of explains the opposite sign, although I really don't like that explanation. You know what I'm saying? Because these two have to be opposites of each other. Just throw the loop to avoid that situation. That's what I do. Okay. Can we, in order to finish this in time, can we talk about RC circuit? This is a differential equation. So what happens if you mix the capacitor and resistor in the same circuit? Okay, right now the switch is open in both sides, so there's nothing. So the current here is equal to 0 in this case. So that's easy to see. But now we'll close the switch to A side. So our current will flow in this direction. Good. Now we'll set up our Kirchhoff's law, starting with the battery. So we gain, right? This is positive side. So we have E. I'm going to put way up there. So E. And then we lose some, right? Across this capacitor. Wow, what was the charge in capacitor? Do you remember? Charge in capacitor was C times your delta V. Right. So your voltage, because that's the voltage drop that we have to calculate, happens to be Q over capacitance. So that's what we put here. Q over capacitance. This is lowercase q that accumulates here because initially there's nothing. But after the positive charges flow through, then it will accumulate here, and then this will push other rest of the positive charges out of that plate, so making this negatively charged. And then currents flows in the beginning, but then it gets harder and harder and harder, and eventually it will come to a stop. That makes sense to you? Because these guys will fight this battery. This becomes a battery, essentially. You know what I'm saying? So if we have to graph this thing, let's try to feel it. Say our Q initial is equal to 0, and of course I initial is equal to 0, right? There's no initial current. And then This is as time goes on, this charge in the capacitor will be some kind of asymptotic. You know what I'm saying? And this will be the whatever the maximum charge you can store. We'll call it Q at the moment, capital Q. Okay? Okay, so that's the differential equations. And then here, you lose some more here. So this is minus IR is equal to 0 according to Kirchhoff's law. Correct? Okay, then. Now I'm going to isolate this and isolate this. What was I again? I was dq over dt. Substitute that, so I have dq over dt divided by c. Can I multiply c on both sides? So that is equal to EC, CE, CE, CE minus and C over CE. I am multiplying C. I'm multiplying R, dividing R on both sides. So this will be E over R minus Q over RC, CR, whatever, right? Do you remember from chapter 6 how I taught you to solve this separable differential equation? Okay. The key is factor this thing out. Then you have Q. Okay, that's easier to separate. But tell me you know how to pick this thing out. Right? You factor this out, so you multiply RC. So multiplying RC, R cancels, so you have CE. You know what I'm saying? Okay. And then now we separate, so dq over q minus CE is equal to negative 1 over RC dt. Good? Now integrate both sides like that. So we have ln, and we are sure q minus CE is equal to negative 1 over RC t plus c. Good? E on both sides. So q minus CE is equal to e to the negative t over RC plus CA. So q minus CE is equal to plus or minus e to the c, e to the negative t over RC. And we come up with a different constant, a, e to the negative t over RC. My a here is plus or minus e to the c, a. Okay, initial condition. What is our initial condition? That, right? So if we put at different color, maybe, at q naught to be 0. Good. Then left-hand side becomes negative CE, and right-hand side, plug in 0 here, so we have A. Oh, A is equal to negative CE. A. So we have Q minus CE is equal to CE e to the negative t over RC. Good. Bring it over, common factor, so Q as a function of t is equal to CE, and then 1 minus e to the negative t over RC. How about that? You get it? Now that graph, it will eventually become as t approaches infinity, right? Do you see this graph right there, asymptotic behavior? This is how you check. This, you plug in 0, 1 minus 1 is 0, check, our 0 here. And then as t approaches infinity, this thing dies, right? So Q approaches CE. So this thingy is same as CE. Is the maximum capacity, the maximum charge you can store. Yeah. here, from here to here. Bring it over. Oh, I forgot. There's a negative sign right there. Right? Because it's negative CE. And then bring it over factor. Good. Nice catch. So this is what it is. Okay? Now the current, so these two are the same thing if you call that Q. Current is the derivative of this, isn't it? As a function of time. So you take a derivative of this dies, so you will have CE and e to the, you have negative e to the negative t over RC. And the chain rule, right? Then you multiply it by negative 1 over RC. You know what I'm saying? And C's cancel, negative signs cancel, so you get E over R of e to the negative t over RC. How about that? So that's what this is. Well then, switch gets thrown to the other side. Now this one is another confusing one, okay? One way, easy way of thinking about it is, well, this is exactly same thing minus the battery as before. So we use this same differential equation, and then you just take away E. That's the easy way out. That's how the book did it. But realistically, the current will flow in different direction. And remember, this was positive side and this was negative side. So is that gaining or losing? You know what I'm saying? But turns out it is still this. Now why? Why is it equal to this? You have to think about it physically. Okay? I'm going to plug in to the other, to bring this to the other side. So this is R times dQ over dt is equal to negative Q over C. And then dQ over dt is equal to negative 1 over RC times Q. You see, capacitor is being discharged. So it is losing charge here. And that is what's creating current. You know what I'm saying? So it has to be opposite sign. Really, remember I said di dt, dq dt is equal to I, right? That is one regular circuit when you're charging capacitor. When you're discharging capacitor, it has to be opposite. You know what I'm saying? So that really this is a double negative sign. So instead of thinking like that, I like to think like this, right? The change of charge here has to be opposite, right? Inversely proportional. The opposite proportional to the negative of this. So this is an exponentially decaying function because charge in the capacitor has to decrease. You know what I'm saying? That's the easiest way to think. Otherwise, this can get real confusing. So if we throw it, say this is Q earlier that we calculated, and then it has to discharge like that. Okay, so here Q original initial condition is capital Q, and then I at initial condition is still 0. Yes.
So this is happening after the.
Yeah, so this is a see from this problem, switch was first thrown into that direction, and then now once the capacitor charges and the current stops, and then you throw it to the other direction. Good? Okay, let's solve this differential equation and call it a day. Okay, so now this is easy after this, right? Because this is already separable very easily, like this, negative 1 over RC dt, integrate both sides, so ln q, and we're still sure, minus 1 over RC t plus c. So absolute value of q is e to the negative t over RC plus c. So q is equal to plus or minus e to the c, e to the negative t over RC. And we call that a again. And then we apply initial condition. So initial condition at Q originally is capital Q now. Then this becomes Q and plug in 0, so this becomes A. And then you get this. Good. And then take a derivative of this, then you get the current. And now if you think about it, you see they're opposite because of the negative sign. You know what I'm saying? Yeah. Now, one thing is this RC shows up so many times, right? So they combine it, and there's like time constant. It's kind of like similar to half-life of the radioactive material. So they just call that tau.